first test method that we'll cover is CE101. This is used to evaluate a device's impact on power quality, specifically its control of harmonic currents and low frequency noise. It's performed on both AC and DC power lines, inputs from a shared platform utility or power bus, and I'll mention here that are not considered part of the EUT, such as a dedicated power source or power supply. CE101 is applicable to Navy surface ships and submarines and has limited applicability for Navy aircraft platforms. The Navy shipboard submarine limits for 60 hertz power shown here are driven by the amount of power the EUT draws during its normal operation. For example, if the equipment draws less than 1 kVA, the limit line drawn between points A, B, and C will be used. Whereas the current draw equal to or greater than 1 kVA will use points D, B, and C across this graph. In each case, that limit will be relaxed based on the amount of actual current being drawn when the current draw is greater than 1 amp. So for instance, when the measurement is made in dB, such as dB microamps, any value over 120 dB microamps, which is equivalent to 1 amp, will be simply added to the limit point, creating a linear extrapolation. Now, CE101 measurements are typically performed using a split core current probe placed around each power line separately. This measurement combines both common mode and differential currents in one scan. It must be stated that excessive background electrical noise produced by the power source can impact these results. Therefore, an ambient background scan is generally required when the test results are found to be within 6 dB of the test limit, even when relaxed or extrapolated. An ambient scan requires that the power source itself be tested without the EUT connected, pulling the same current draw roughly as the equipment under test. The results of the scan must show that the power source emissions are at least 6 dB below the limit. And then when the ambient control is common issue with the programmable power supply, switching power supplies are used. So in these cases, correction filters are usually installed to combat non-compliances. We'll talk a little bit about that later on here. So correction filters for CE101, current harmonic correction filters, are also used to correct current harmonic issues within the EUT. They come in a number of flavors which could be selected carefully. Inductive reactive filtering is by far the most common solution used simply due to the simplicity and flexibility. This requires an addition of series inductance is added to each power line. And that reactance value is based on the maximum EUT current draw and commonly specified as a percentage of voltage drop at the fundamental current. Reactance impedes the flow of current, much like a resistor, varies based on frequency. So the higher the frequency, the higher reactance. And essentially, an inductor is a low-pass filter, and they are generally bulky as well as heavy and can produce heat depending on the size and the amount of current that it's passing. So these factors must be accounted for in the overall design of the system. The second is a harmonic trap filter or band reject filter. And this is a combination of an inductor and a capacitor, which both provide reactive elements configured to attenuate a particular frequency when allowing all other frequencies in the range to pass freely. These devices are tuned based on the load impedance of the EUT and are exceptional at targeting an out of compliance harmonic when the current draw remains constant and doesn't fluctuate. However, when variance in load impedance is common, you will see that this tuned resonant frequency in the trap filter will shift, causing a degradation of its effectiveness. And an active harmonic filter is essentially creates and applies an inverse representation of that harmonic current back onto the power source. A cancellation of this occurs, significantly improving the harmonic control. Low due to the active components in these types of circuits, they are frequency limited and compared to a passive low frequency circuit. and may require additional high frequency filtering. Additionally, these devices are more expensive than passive filter options, and due to the active components again, they may have an impact on the life expectancy of the device. So really some pros and cons to each one of these, and really that information should help decide the use of a particular filter in one of your applications. Now the second method here is CE102. This measures the conducted voltage emissions produced by the EUT and coupled onto the platform power utility lines. Again, power sources not part of the EUT. And CE102 is applicable to all platform installations and procurement agencies across the board. Now the CE102 limit is comprised of one basic curve, which is relaxed based on the input voltage level. So for example, the 28 volt system just uses that basic curve here. But if the system is drawing 115 volts, the 115 volt limit would basically relax that 28 volt curve by 6 dB, as well as 12 dB by 440 and so forth. Now the drawing you see here is a typical CE102 setup. This depiction, you can see the input voltage waveform produced by the power supply is pretty noisy. I drew this really to kind of show that switching noise of that power supply is usually unregulated and won't meet the MIL-STD-461 criteria in general. So as discussed earlier, it's pretty common and usually requires the use of a low pass filter to meet ambient requirements. These are depicted as facility power line filters mounted to the wall of the EMI chamber. And a representation of the clean power waveform is shown on the other side of this, being fed into the LISN. And from the LISN, source is connected to the EUT. To the far right, inside the EUT, you see another representation of that power waveform. This is distorted, basically depicting inherent operation of the internal equipment. So it's common, therefore, to see EMI power filters installed at the primary entry point to the equipment under test as well, in order to meet CE102 emissions criteria or control limits. Now, to describe what a LISN is, a line impedance stabilization network is simply an artificial impedance network installed between the input power line in the EUT. This impedance represents approximately 50 meters worth of power distribution wiring present on the platform installation. The added impedance here stabilizes the measurement results between the different test facilities as well. Now, 50 microhenry LISN schematic shown here in the upper right drawing depicts a 50 microhenry inductor in series with the power source. And then an 8 microfarad capacitor is tied to grounds through a 5 ohm resistor before that inductor. This really provides an impedance match at 10 kilohertz. On the other side, you'll see a 0.25 microfarad capacitors tied to ground through a 1 k ohm bleed resistor. And that voltage, a voltage measurement is made there to determine CE102 conducted emissions being fed back from the EUT. The impedance curve shown just below this represents the typical characteristics of a 50 microhenry inductor across its frequency range from 10K to 10 meg. As you can see, it's fairly ineffective at low frequencies, but the impedance increases as you get higher in frequencies. Now, although the majority of the items that are tested at 461 will utilize a 50 microhenry LISN, there are applications where this may not be representative of the platform installation. In cases where using a 50 microhenry LISN may impact the operation of the EUT. For example, a low source power impedance for a high current, low voltage switching power supply may have trouble regulating or even turning on with the presence of a 50 microhenry LISN in line. In this example, that power source may be designed for a land vehicle platform or a small fighter aircraft for shorter power lead lengths. Therefore, a smaller LISN value such as 5 microhenries might be more appropriate. 5 microhenry LISN are commonly used in commercial aerospace testing such as RTCA DO-160, which are that whole series of tests are covered by another video series. However, the use of a different value listen must be identified in the EMI test procedure along with the engineering judgment for the change. Now, regarding filters, and it's important to note that an EMI power line filter is to pay close attention to the design cutoff frequency. This is specifically important when commercial off-the-shelf equipment known as COTS are integrated into a subsystem. These devices are designed for commercial applications such as a home, office, or light industrial environment, and as discussed earlier, vary significantly from a military platform environment. So in regards to conducted emissions, the FCC 47 CFR Part 15 requirements for the United States and the CISPA requirements for Europe both start at 150 kilohertz, whereas MIL-STD-461G starts at 10 kilohertz. This means that the commercial low-pass power filter is designed to attenuate frequencies above 150K while allowing lower frequency energy to pass freely. Therefore, there's an option here, an ability for electrical noise produced by the EUT in the 10 kilohertz to 150 kilohertz range to cause compliance issues with the CE102 test limit. In these cases, the EMI filter is either swapped out or additional filtering is added to that filter to shift its cutoff frequency to a lower frequency range.